In this video, I'll be teaching you how to identify orthopara and meta-directing groups without memorizing the chart. So in the last video, I showed you this chart for identifying orthopara directing groups. What is something you notice that all these directing groups have in common? And the answer is lone pairs of electron. So for instance, as you can see here, NH2 has lone pairs of electrons. So does this molecule and all these halogens, right? However, if you look here, these methyl groups do not have lone pairs of electrons. But if you think about it closer, if you remember, any of these methyl groups have hydrogens on it. For example, this R group. Let's say it's some kind of methyl chain attached to some kind of benzene ring, right? This methyl chain has hydrogens attached, right? And if you kind of remember, these hydrogen kind of donates electron density. So in that sense, yes, it does kind of quote-unquote have electrons. In addition, something I want you to notice is that in this chart, this top row is the most orthopara directing group, followed by this, this, and this. As you can see, this is indicated by this arrow. So if you remember from the last video, I showed you this chart to identify meta-directing groups. What is something that all these groups have in common? The answer is some kind of plus charge. So as you can see here, this carbon has a partial positive charge, and same with all the rest. In addition, this sulfur has this partial positive charge, and all these molecules here also have either a full positive charge or a partial positive charge. In addition, something I want you to recognize is that all these four groups are more meta-directing groups than these top two, which is identified by this arrow. So in regards to identifying the strength of orthopara and meta-directing groups, unfortunately there really is no good way to realize which orthopara group is stronger than other orthopara groups. However, there is a trick to identifying which meta group is stronger than other meta groups. So for example, we have some kind of benzene with some kind of carboxylic acid versus this benzene with an NH3 group on it. So if we look at this carboxylic acid on this benzene group, one thing I want you guys to realize is that this oxygen has, two lone pairs of electrons. But you kind of have to remember that this can undergo some kind of resonance structure. More specifically, this electron can go onto the oxygen, thus forming this resonance. So as you can kind of see, this carbon is in the intermediate between both positive and neutral charge. So because of that, this central carbon is partially positive, and that's usually indicated by this kind of signal. In comparison, NH3 on a benzene ring has a full positive charge, as you can see. And the reason for this is because nitrogen usually likes to have two bonds with a lone pair of electrons like so. But because this has three hydrogens and a fourth bond on the benzene, I'll put Be for benzene, right? Because it has four groups, the nitrogen indeed has a full positive charge. So when we compare this full positive charge to this partial positive charge on this carbon, a full positive charge is stronger. So because of that, NH3 is a more stronger electron withdrawing group than this carboxylic acid, which we can see in this chart over here. So in summary, when identifying orthopara versus meta-directing groups, in order to identify orthopara groups, you have to look if the molecule has extra electron donating pairs. Conversely, for meta groups, you have to identify if the group has a positive charge, whether it doesn't matter whether it's full or partial. In addition, full positive charge are stronger than partial positive charge. Thus, anything with a full positive charge is more meta than partial positive.